Hello, and welcome to Differential Equations. This is Lecture 6, Exact Equations. Last time, we talked about integrating factors. So what we talked about was how multiplying the equation dy by dt plus p of ty equals q of t by the exponential of the integral of p of t dt turns it into, well, e to the integral of p of t dt dy dt plus e to the integral p of t dt times p of t y is equal to e to the integral p of t q of t, and this left-hand side is d by dt of a single function, namely e to the integral of p of t dt times y. Right? And because this left-hand side has become the derivative of a single function, the equation is now really easy to solve. At least in principle, because all you need to do is integrate both sides of the equation with respect to t. This time, we're going to talk about exact and other special first-order equations. Okay, so suppose we had some function, say n of x and y, dy by dx, plus m of xy. Right? Suppose we had this differential expression, right? And just like over here, what we did last time, it would be really convenient if we could interpret this as the derivative with respect to x of some function, right? So we can ask, when is this equal to the derivative with respect to x of a single function, call it psi, of xy, right? Okay, right? So this would be great because it would really simplify any differential equation that had this as a left-hand side, right? Just like we saw last time. Okay, well, we'll figure out when this happens in just a second, but let's give it a name. In that case, we say that this expression, n of xy dy by dx plus m of xy is exact. And we call this function psi the potential function. Right? So, for example, e to the integral of p of t dt times dy dt plus e to the integral of p of t dt times p of t y is exact with potential function e to the integral of p of t dt times y. Okay. So Well, what can we say about this so that we can compare it to this? From the chain rule, we know that the derivative with respect to x of psi of x comma y, right? When we think of y as being a function of x, the chain rule tells us that this would have derivative d psi dy of xy times the derivative of y with respect to x plus d psi dx. So if the expression n of x comma y dy dx plus m of x comma y is exact, we need to have just comparing terms, n of xy needs to be the derivative of psi with respect to y, and m of xy has to be the derivative of psi with respect to x. Okay, now from vector calculus, we know that mixed partials of functions, sufficiently nice functions anyway, are equal, right? So we know that the second derivative of psi with, if you differentiate with respect to y and then with respect to x, is the same as the second derivative you differentiate in the opposite order. So we need to have that the derivative of n with respect to x, well, that would be the derivative with respect to x of the derivative of psi with respect to y. So that would have to be equal to derivative in the opposite order, first with respect to x and then with respect to y, but that's the derivative of m with respect to y. So if this expression is going to be exact, then these functions have to have these derivatives equal to each other. Now, it turns out that as long as we're working on a simply connected domain, right? So simply connected domain is something like the unit disk. This condition is also sufficient. Thus, the expression n of xy dy by dx plus m of xy is equal to derivative of psi with respect to x for some function psi, right? Say on the interior of the ball in R2, if and only if derivative of n with respect to x is equal to derivative of m with respect to y. This is often written in differential form notation. Right? So what we say is that the form n of xy dy plus m of xy dx is exact if it is equal to the psi, right? This is sometimes called the total derivative of psi, or the exterior derivative of psi. And this is the differential form that has coefficients d psi dy times dy. That's the coefficient of dy, plus the coefficient of dx is going to be d psi dx. For some function psi. And this happens, again, as long as we're on a sufficiently nice domain, this happens if and only if the derivative of n with respect to x is equal to the derivative of n with respect to y. Okay, before getting to some examples, let me point out that exact equations usually only give implicit solutions. For example, if n of xy dy plus m of xy dx is exact with potential function psi, then the solution to n of xy dy plus m of xy dx equals 0 is, well, that's the same equation as d psi equal to 0. And so the solution is psi of x comma y equals a constant. Right? So this gives us a relation between x and y, right? It gives a solution curve, but it doesn't necessarily give us y as a function of x explicitly. Okay, so let's work out an example. Suppose we want to solve 1 over y dx minus x over y squared dy equal to 0. Right? So first thing we ask is this exact? Right? And given that the class is about exact equations, you won't be surprised to learn that it is. But let's check. Right? So is this exact? Well, here, the coefficient of dx, that's m, is 1 over y. The coefficient of dy, that's n, is minus x over y squared. And if we take the derivative of m with respect to y, we get minus 1 over y squared. And when we take the derivative of n with respect to x, we get minus 1 over y squared. And since these coincide, we see that this differential form is exact. Okay, so that guarantees that there is a potential function. So let's find one. Okay, so this should satisfy that the derivative of psi with respect to x is equal to m, so that is 1 over y. And the derivative of psi with respect to y should be equal to n, which is minus x over y squared. Okay, so we take either one of these, and we just integrate both sides. So let's start with the derivative of psi with respect to x is 1 over y. So if I integrate both sides with respect to x, what I get is psi equals integral dx over y, right? I'm integrating with respect to x, so 1 over y is just a constant. So this is x over y plus some constant. Okay, but now this is key. This constant is a constant that could depend on y, right? So it's a constant with respect to x, but it's not necessarily a constant with respect to y, right? Because this is just our ambiguity when we're computing this antiderivative with respect to the x variable, right? And so a function of y would have 0 derivative with respect to x. So it counts as a constant as far as this integral or this antiderivative computation is concerned. Okay, so using this equation, using the information we had about the derivative of psi with respect to x, we have determined psi up to a function of y, right? We still need to determine this function of y. The way we do that is we take this equation, well, this expression we found for psi, and we plug it into this second equation. Right, so the second equation says the derivative of psi with respect to y, right? So from what we know, this is the derivative with respect to y of x over y plus f of y. So that's equal to minus x over y squared plus the derivative of f with respect to y, right? On the other hand, we know that it's equal to minus x over y squared. So from this equality, you see that the derivative of f with respect to y is 0, and f is a constant, right? Notice that now it really is a constant, right? Because we already knew from here that it didn't depend on x, and now we know that it doesn't depend on y. So what does that tell us about psi? Psi is x over y plus some constant, and the solution to the equation x over y is a constant. And in this case, of course, it would be very easy to solve for y. Let's do an example where it wouldn't be so easy to solve for y, and we only have the implicit. Suppose we want to solve dy by dx is equal to minus e to the y over x e to the y plus 2y with initial condition y of 0 equals 1. Okay, if we rewrite this, using differential forms, we get the equation x e to the y plus 2y multiplying dy plus e to the y multiplying dx is equal to 0. Okay, so then first we ask, is this exact? Well, here the coefficient of y is n is given by x e to the y plus 2y, and m, the coefficient of dx, is e to the y. So the derivative of n with respect to x is e to the y. The derivative of m with respect to y is e to the y. So it is exact. Next, we want to find a potential function psi such that the derivative of psi with respect to x is equal to m, so it would be e to the y. The derivative of psi with respect to y is equal to n, right? So x times e to the y plus 2y. Okay, so we could start now by integrating either one of these equations. Of course, you want to pick whichever one is simpler. So let's start with the first one. Integrating the first equation with respect to x, we get that psi of xy is equal to, well, if I integrate e to the y with respect to x, I just get x times e to the y, right? And then plus a constant, but just like before, this constant is an arbitrary function of y. We now substitute this into the second equation. We get that the derivative psi with respect to y, okay, well, if I differentiate this with respect to y, I get x times e to the y plus the derivative of f with respect to y. On the other hand, we already know that the derivative of psi with respect to y is x e to the y plus 2y. And comparing these, we see that the derivative of f with respect to y is 2y. So f of y is equal to y squared plus some constant. Thus, our potential function is x e to the y plus f of y, but f of y is y squared up to some constant. And the general solution is x e to the y plus y squared is equal to a constant. Okay. Now, in this case, we were given an initial condition, so we can use that initial condition to find the constant, right? So we were told y of 0 is equal to 1. So we can find C using our initial condition. Right? So we know that this, we're looking for the curve that goes through the point 0, 1. Right? So if we plug in x equal to 0 and y equal to 1, we get on the left-hand side, we get 1. On the right-hand side, we get C. So finally, we conclude that x e to the y plus y squared is equal to 1. Right? And notice that here, we cannot just solve for y. Not easily, anyway. Okay. There are some other tricks that it's worth knowing. For solving first-order ODEs. One trick is just making a good substitution. So what makes a good substitution? Well, for example, if your equation has the right-hand side, which is a function of y times t, as opposed to y and t individually, then you might try using a new variable v equal to y times t. If dy by dt is equal to a function of y over t, then use v equal to y over t. If dy by dt is equal to a function of y plus t, right? So y and t don't appear individually on the right-hand side, except in the combination y plus t. Well, then try the change of variables v equals y plus t. Similarly, if dy by dt, if the right-hand side is always a function of 2y plus 3t, then use v equal to 2y plus 3t, right, etc. Right? If the right-hand side, you notice that y and t always enter in the same linear combination, well, then make a change of variables and use that linear combination as your new variable. Right? So let's do an example. Right? Suppose we started with t times dy by dt is equal to y times natural log of t minus natural log of y. Okay, well, at first this doesn't seem to apply to any of these good substitutions, but we can rewrite this using properties of logs. So dy by dt is equal to y over t times the natural log of t over y. So we see that it's this situation, and so we should try this change of variable. So we see that v equal to y over t might help. Okay, if v is equal to y over t, then y is equal to v times t. So the derivative of y with respect to t, right, from here, we can just use the Leibniz rule and write this as t times the derivative of v with respect to t, plus v times the derivative of t with respect to t, which is just 1, on the one hand. On the other hand, we know the derivative of y with respect to t is equal to this. And if we rewrite that using v, we see that this is equal to v times the natural log of 1 over v, right? Or another way of saying that, it's minus v times natural log of v. Thus, if we now solve for the derivative of v with respect to t, we see that this is equal to minus v times natural log of v plus v, all of that divided by t, and this is separable, which means we're in really good shape. We know how to solve separable equations. Here's another example. Suppose we're looking at dy by dt is equal to 4t minus y plus 1 squared. Okay, so we look at the right-hand side, and we see that t and y always occur in the linear combination 4t minus y. So we see that v equal to 4t minus y might help. Okay, well, if v is equal to 4t minus y, then y is equal to 4t minus v. So the derivative of y with respect to t is equal to 4 minus the derivative of v with respect to t. On the other hand, the derivative of y with respect to t is equal to this. So if we write this using our new variable, we see that it's v plus 1 squared, right? So now if we solve for the derivative of v with respect to t, see derivative of v with respect to t is equal to 4 minus v plus 1 squared, right? And this is separable. Which is great because we're really good at solving separable differential equations. Okay, so again, these are tricks because in general, if you just write down a random differential equation, odds are good that you won't be able to solve it explicitly, right? There are only a few equations that we know how to solve explicitly. So mostly we collect some tricks as far as explicit solutions go. What happens in the real world is if you end up with a differential equation, unless you're really lucky and there's a trick you can use to solve it explicitly, you're mostly going to be trying to figure out qualitative properties of the equation without being able to write down an explicit formula. But because there are so few that you can solve explicitly, we keep track of these tricks, and sometimes we give them names. For example, the second one is known as the Bernoulli equation. So here's this trick. Suppose you have an equation that looks almost the same as the linear first order differential equation, except that here, instead of just having q to the a, q of t, I have q of t times y raised to some power. And this a is not equal to 0 nor 1, right? If a was equal to 0, then we'd be in the linear equation, right, in the standard form. If a was equal to 1, then it'd also be a linear equation. It's just this term should be combined with this term, right? So here we're interested in what happens if a is not equal to 0 and not equal to 1, right? So here's the trick. Rewrite this equation as y to the minus a dy by dt plus p of t times y to the 1 minus a equals q of t. And then use the new variable, let's call it w, equal to y to the 1 minus a to get a linear equation. Right, so it's easiest to just see this in practice. Here's an example. Let's consider dy by dt equals 5y plus e to the minus 2t times y to the minus 2. Okay, so let's rewrite this as y squared dy by dt minus 5y cubed equals e to the minus 2t. And once we've written this way, we use whatever's multiplying the p, right? So in this case, y cubed. W is equal to y cubed. Okay, so if w is equal to y cubed, notice that then the derivative of w with respect to t is equal to 3y squared times the derivative of y with respect to t, right? And y squared times the derivative of y with respect to t is exactly what shows up here in the first term. So this equation becomes Okay, so y squared dy by dt from here is going to be, move the 3 to this side, 1/3 dw by dt. Then the next term, minus 5y cubed. Well, y cubed was w, so it's going to be minus 5w. And then the right-hand side just stays the same, e to the minus 2t, right? And this is a linear equation. For w. And we've already studied how to solve linear first-order differential equations. So if we reduce this problem to one we already know how to solve. Okay, next trick. This trick is called reduction of order. So sometimes a substitution will let us use first order methods to solve second order equations. Okay, so how does that work? The general second order equation, second order ordinary differential equation, has the form capital F of t, y, dy by dt, second derivative of y with respect to t equal to 0. Right, so you have your independent variable, your dependent variable, and the first two derivatives of your dependent variable, right? And some relation between them, this capital F, is equal to 0. If either the y or the t are not explicitly present, then we can simplify and use first order methods. Okay, so let's think of this through examples. So first example, let's consider the equation t times the second derivative of y with respect to t minus derivative of y with respect to t equals 3t squared. Okay, so notice that here we have t is showing up, and y only shows up through its derivative and its second derivative, right? It doesn't show up on its own. So here, the y is not explicitly present. So what you want to do is think of this as being an equation, not for y, but for dy dt, right? If you think of this as being your dependent variable, then only one derivative of it shows up. So you've ended up with a first order differential equation just for the derivative of y with respect to t instead of y. So a nice way of carrying that out is to simplify using v, a new variable. V is dy dt, right? If you use that variable, then we can rewrite this as t times the derivative of v with respect to t minus v is equal to 3t squared. right? Or equivalently, if we solve for dv dt, we end up with 3t squared minus v over t. Right? This is a separable equation. So we can solve for the function v, and then use the derivative of v with respect to t is equal to y. Sorry, the other way around. V is equal to the derivative of y with respect to t to solve for y, right? So perfect. So in this case, for this equation, we'd be able to find y by doing these two steps. In general, there's no guarantee you'll be able to solve for y. But what is guaranteed is that if y doesn't show up, right, but only its derivatives, then you make this substitution and you reduce the order by 1. Now you only have to solve a first order equation. Okay, that's one of these cases when the y doesn't show up explicitly. Next, let's look at the case where t doesn't show up explicitly. What can you do then? So let's consider an equation like second derivative of y with respect to t plus k squared y is equal to 0, right? So here the t doesn't show up explicitly. Right? It only shows up here where we're denoting that the derivatives are taken with respect to t, right? But this equation doesn't have any t showing up. So what you want to do in this case is think of y as being the independent variable and then make the same change of variables as we did in the previous example. So y will be the new t. Let's think of y as being the independent variable. And replace dy by dt with some function p of y. Okay? So we can rewrite second derivative of y with respect to t. Well, this would be the derivative of p with respect to t, right? We want to think of p as a function of y. So to compute its derivative with respect to t, we use the chain rule, right? So this would be derivative of p with respect to y times the derivative of y with respect to t, right? But the derivative of y with respect to t, we just agreed that's equal to p. So this would be p times the derivative of p with respect to y. Okay? Substituting that in, right? Where here we had second derivative of y plus k squared y is equal to 0. Now we have p times the derivative of p with respect to y plus k squared y is equal to 0, right? And we can rearrange this as derivative of p with respect to y is equal to minus k squared y divided by p. Right? Now, this is separable. Right? This separable equation where, remember now, y is the new t, and then p is the new y, right? So p is the function of y that you're trying to solve, and here you have a differential equation for it. Right? For this particular equation, we ended up with something separable. So then we can solve for P, and then use that P is equal to dy dt, solve for y, right? Again, that's just for this particular equation, we ended up with something separable. There's no guarantee that that will happen for a general second order equation. What is guaranteed is that if you have a second order differential equation and the t doesn't show up explicitly, then you can change your point of view, think of y as being the independent variable, make this change, and you will end up with a first order differential equation, which hopefully you can solve, and then use this relation to solve for y. Okay, we'll stop there and pick it up from there next time.